And our next speaker is Lander, who's going to be giving another very exciting Tensor Network talk. And just while Lander's setting up, keep in mind like the BOF and poster session is right after this. So if you have more questions for the speakers or want to chat about something, keep that for the BOF. And we're anticipating that we'll actually have the BOF discussions in a corner near the poster session so that everyone can actually eat some food at 6. Because I don't know about you, but I'm kind of hungry. So yeah, stay tuned for that. And in a moment, we'll hand it over to Lander.
Oh, I apologize. Oh, everyone was eavesdropping on me.
No, you would have heard yourself, but.
No problem. Less than 50. All right, great success. Okay, hi everyone. Thanks for having me. I am Lander, currently doing a PhD at Ghent University, and I'm here to talk about tree sweeping algorithms with ITensorNetworks, which I should say is work that I started partly while interning with Ash in Pasadena, and then I continued to open source it kind of by myself. So since it's already been an hour or two, I'll start with like a quick flash of what ITensorNetworks is and what the goals and challenges for such a general network package are. After that, we'll just try to avoid most of the challenges and just restrict ourselves to trees. And I'll give you an overview of the interface for the tree tensor network solver in ITensorNetworks.jl, which I implemented, and how you can use it, as well as give some highlights of implementation, which could have use either when you're using the package or elsewhere. And then I'll end with some plans for the future. So ITensorNetworks.jl, which I added a part to, is a toolbox for general network tools on top of ITensors, which aims to provide a simple and intuitive interface for some of the more advanced or unclear network structures and algorithms. And so, well, if you want to know about it, you could just rewatch Matt's talk, but in essence, it's just a package that allows you to define tensor network states on general graphs and manipulate these in all kind of fancy ways, as well as print out nice Unicode plots. And so this is developed by Matt, Joey, Linjian, Miles, and to some degree, myself. So if you have general network structures, you could basically use this to do whatever you want, such as like optimize any cost function you could think of, but there's also more physics-inspired applications such as ground state searches and time evolution. And so when working with general networks, the immediate problem you run into is that you cannot contract these efficiently in general. So the main goal of any general network package should be to find ways around this. And so within ITensorNetworks.jl, you have Linjian working on approximate contraction routines for general networks, and you have Joey working on approximate evolution algorithms who are fighting the real fight. And so what I will be talking about is not that. I will be restricting to classes of networks that you can actually contract exactly, which is just states defined on loop-free connected graphs, also known as trees. And so these have been quite well studied, and they have certain nice properties which allow you to define robust local update routines, which we call like sweeping algorithms, in which you basically like move through the tree and just update local patches in a certain way, depending on what algorithm you're actually trying to run. And so specifically for the 1D case, for matrix product states, there's actually a lot of good open source implementations for all these kinds of things, 2 of which we've already seen today, and there's many more. So within ITensors, for example, there's ITensors.TDVP, which you can use to do ground state searches, excitations, time evolution, and approximation, all with a kind of nice common interface. And so what I did is just to take all of these routines from ITensor.TDVP and generalize them to arbitrary tree geometries within ITensorNetworks, with the hope of retaining all the nice robustness of your known and loved MPS algorithms, while still having some way to tailor the network to your system geometry a bit more. And so, well, the basic goal of my talk is to just show how you can do what you were already doing using ITensorNetworks, and how you can do things that maybe you weren't doing using exactly the same interface. All right, so if I want to demonstrate this interface, let's just dive in with an example. So what I'm doing on the left-hand side here is just finding the ground state energy of some spin model on some nice tree using DMRG. So how do you run DMRG on a tree? It's not very hard. There's a few steps. You just define your system geometry as any tree graph. You can build whatever you want. You can define the Hamiltonian of your system in a nice, neat symbolic way using some system from ITensors. More on that in a bit. Then all you need to do is automatically convert this into a tree tensor network, which is just a built-in routine. And then you just run DMRG with your favorite parameters for how long you like. And so for the people who've used ITensors, they might notice that this just looks scarily like the built-in DMRG routine, which is the entire point. It's supposed to be easy to use. All right, so the main star of the show is basically how easy it is to define Hamiltonians on general trees. And so this is done via the ITensors opsum system, which is just a lazy algebra system for defining Hamiltonians as lazy sums of tensor products. So just starting from any graph, the interface is very easy. You just loop over sets of vertices, for example, the nearest neighbors or the next to nearest neighbors, and you just start adding stuff to the Hamiltonian, where you have kind of your favorite prefactor, and then for every operator in a tensor product, you write down the operator and just the site it acts on, and this kind of accumulates in a symbolic way, and this gives you your Hamiltonian. And then all you need to do is pass this to the tree tensor network constructor that I've built, and then also pass in the layout of the physical systems in your thing, and then it just automatically compresses it into an operator of the right form. And so it's just really easy to use. And so a second feature of this framework is that basically the interface is the same for any sweeping algorithm you want to do. So say instead of finding ground states, we want to do time evolution, then all you do is change the acronym DMRG for TDVP. This switches out the local solver from like solving eigenvalue problems to doing exponentiation. And so you can do time evolution on exactly the same system, and now all you just do is change this four-letter word, and instead of specifying how many sweeps you want to do, you just find some time and some time step, and then it just runs it automatically. And so, well, that's basically the gist of the interface. If you want more examples of what you can do with this, I would guide you to the actual repo of ITensor Networks, but I also attached some more narrated examples as notebooks in the description of my talk. And so now I'm just going to go on a small tangent on things I like, which might actually be useful in other settings when just not doing this. So the first thing I like is a Hamiltonian representation. So you might wonder how I could just take this symbolic expression and automatically compress it into something of the right shape. And so I'm not going to explain how this works, but basically what we do is we first go via a fully symbolic representation as a network of like sparse tensors, where each of these sparse tensors on a vertex encodes what operators act on that vertex and how they connect to all the other stuff. So how this happens is through some finite state machine logic, and it's not really that important. But you just get some network of block tensors, let's say, that if you contract it, it just spits out the full Hamiltonian. And so currently this is not used. We just compress this into a dense operator. But there are settings where this is just kind of a neat thing to do. I know in Ghent we very much like this, and Lucas is working on like a toolkit to work with these block tensors. So I thought this was a nice place to just plug this as something that you might be able to do. And then a second thing, which is actually more for the users or the potential users, is that you can customize these sweeping routines to not just do what I let you do, but to do whatever you want in two different ways. So if you don't do anything, I will just decide how to sweep through the tree in some predefined way, and this usually kind of works quite well. But there's often situations in which you just know that there's a better sweeping pattern, or you don't want to do this in this specific region, and so you just want to do it your own way. So Miles actually recently added support for providing your own custom sweeping regions. And then something at least equally useful is that, so for all the standard algorithms we export, we have just default local solvers which tell you how to update your local tensors in a patch, and then this is carried on. So say you want to do something else that we haven't defined, it's very easy to supply your own local solver, which is just like called in this way. So as long as it adheres to the right interface, you can basically use this to do whatever local update you want. One major thing you could do with this is just, for example, for time-dependent problems, you can kind of hack the time dependence into this local solver, and then this gives you a way to do it. So there's also an example linked in the talk description on this. And so, well, that's basically it. So in ITensor TDVP, starting from a while back, you now have all the familiar MPS-like solver capabilities, such as simple and intuitive Hamiltonian construction, some default 1- and 2-site sweeping patterns on general trees, and default local algorithms for all the default local solvers for all the algorithms you already know, as well as some new support for just customizing things in whichever way you want. And so I will end with some plans for the future. So the first very obvious one is just like to put in all this stuff that needs to be in there. So there's no symmetry support so far because no one's really gotten to it. There's no real obstruction there. We just need to do it. And what would also be nice is to like export some more tools for easy customization, so you don't have to know so much about the internals to actually just adapt things to your setting. And so some exciting new features which are worked on by people who are not me are like custom dynamic sweeping patterns, where instead of like fully specifying a sweep, you just kind of customize it a little bit using some logic, which is being worked on by Miles. And then Benedict and Vladislav are working on some efficient subspace expansion algorithms, which are just better or cheaper than 2-site updates, which for trees can get just very expensive very quickly. And then I will end with a blanket statement on applications, the basic gist of which is, I mean, this is just now here. So anything you are currently using MPS for as a approximate backend for your solvers, you could just try to use trees, either for systems that actually have a tree-like geometry, or you could kind of hack it and find the best spanning tree for your system and just run it anyways. And there will be settings in which this just works better. And so with that, I will end and leave some more time for Joey, who is also going to talk about a different part of ITensor Networks.
All right, so while Joey comes in and sets up, we have time for one quick question and answer, if anybody has one. All right, Ash, put your hand up first, so you're getting to go.
All right, thanks, Sander. I wanted to ask, you mentioned compression of the operators. So, like, how efficient is the operator representation these days? Like, if you give it simple...
But so
I guess nobody can hear you, apart from us in the room.
Yeah, so it's definitely better than it was. I think it's about as good as you can get, in the sense that it's doing exactly the same thing now that it was doing in the default iTensors thing. So I think there's the same issue where for just, if you have a single on-site operator, it'll still be too big. It'll be a bond dimension 2 instead of 1. But other than that, there is like manual symbolic SVD compression going on now. So it's a lot better.
Cool. No,
it's not numerical anymore.
That's very nice. Thanks.